In this lesson, we're going to be talking about the idea of continuity. And I've typed up a definition of continuity, but basically, if a function is continuous, it just means you can draw it with a pencil without ever lifting up your pencil. So there's no breaks or gaps or holes in it. A little bit more formally, for a function to be continuous, it has to be defined. So there has to be a point. You can't have an open circle. The limit as x goes to c of that function has to exist as well, and those two things have to be the same. There can't be any jumps or gaps. And so rather than focusing on that kind of formal definition, let's just see how this works with an example. In example 1, we are going to determine if the function is continuous at each point and explain why. So at x equal negative 2, the function is continuous. It's continuous there because we could say that the limit as x goes to negative 2 is equal to the function value f of negative 2. In other words, as we approach x equal negative 2, that part is the limit, we get the same thing as where the little point is. At x equals 0, the function is not continuous. It's not continuous because there's a hole there. Another way of saying that is it's not continuous because f of 0 is undefined. That would be our kind of formal way of saying, well, there's a hole there, so it's not continuous there. I guess I should write not continuous, and then the first one, I said it, but I didn't write it. It is continuous. Okay, finally, part C at x equal 2, the function is not continuous. It's not continuous because there's a jump in there, but how we could describe that is we could say that the two-sided limit doesn't exist. If you approach x equal 2 from the right and the left, you get something different. That's how we would describe a jump in the graph. So because that limit doesn't exist, there's no way the limit can equal the function value, and therefore it's not continuous at x equal 2. Now we're talking about continuity because many of the theorems that we're going to develop in calculus only apply to continuous functions. So what kinds of functions are continuous? Well, the answer is most of the functions we're going to deal with are continuous on their domains. Polynomials are continuous everywhere. They have a domain of all real numbers. Rational functions are continuous on their domains. And remember, for rational functions, we said that the denominators can't equal 0. Radical functions are continuous on their domains. For radical functions, we said the thing inside the square root or the radicand has to be bigger than or equal to 0. Exponential functions are continuous everywhere, and logarithmic functions are continuous on their domains. And for logarithms, we said that that thing inside the logarithm, I'm going to call it the argument, has to be bigger than 0. So basically, all of the functions we work with are continuous on their domains. So in example 2, if you're asked where is the function not continuous, you're basically finding the domain. This function is going to be continuous on its domain. Now, to find its domain, I have a rational function, and so I know that the denominator can't equal 0. 2x minus 1 cannot equal 0. I can solve this for x by adding the 1 and then dividing by 2. So the domain of this function is x, every single number except for x equal 1/2. And so where is this thing not continuous? It is not continuous at x equal 1/2. And in fact, because this is a rational function, that 0 of the denominator is actually a vertical asymptote. And that's why it's not continuous there. There's some kind of jump in the graph at that point. Where is the following function continuous? G of x equals square root of 5 minus x. Radical functions are continuous on their domains. So if I want to find the domain of this, I take the thing inside the radical, and it has to be bigger than or equal to 0. I can solve by subtracting 5, and then I'm going to divide by negative 1. But if we divide an inequality by a negative number, we have to flip the direction of the inequality. And so the domain of this function is actually x less than or equal to 5. Everything from negative infinity to 5. This function is continuous on its domain. So it would be continuous on that interval negative infinity to 5. The function doesn't exist outside of that domain, and so I guess you could say it's not continuous from 5 to infinity because that's not its domain. Now, we have to put a little bit more thought into these problems when we're given those piecewise defined functions. So if it's not a piecewise defined function, really we're just finding the domain. That's what we did in parts A and B. In part C, if we want to answer a question about continuity, because we have three pieces, we have a line, a quadratic, and a line. Each piece is individually continuous. Lines and x squareds, parabolas are continuous. But we need to know if the pieces actually line up. And so we're going to check kind of the endpoints of the pieces to see if they line up. Okay, so when x is less than 0, we use this first definition, 2x plus 1. So that means if I want to find the limit as x goes to 0 from the left of this function, I am talking about x values that are smaller than 0. So again, I'm going to use that first definition. To find this limit, I could plug in 0 for x. I get 2 times 0 plus 1, or 1. But if I approach x equals 0 on the right, if I want to find the limit of this function as x goes to 0 from the right, now I'm x values that are just a tiny bit bigger than 0, and now I'm using that middle definition. So I'm going to plug 0 into x squared, and 0 squared is 0. Because these two numbers are not the same, that is what tells me the two pieces don't line up. Or more formally, you could say the limit as x goes to 0, that two-sided limit, doesn't exist. This tells me that this function is not continuous at x equals 0. Again, the two pieces don't line up at x equals 0. The piece on the left goes to a y value of 1, whereas that piece in the middle goes to a y value of 0. Now, we can do the exact same thing at x equals 3, which is kind of the other break in the function. If I want to approach x equals 3 from the left, I now have x values that are a little bit smaller than 3. So if my x values are less than 3, I'm in this middle piece, and I am going to plug 3 into that x squared, and that gives me 9. If I approach x equals 3 from the right, my x values are now just a little bit larger than 3, and now I'm using that bottom piece. And I'm going to plug 3 into the x plus 6. Oh, and that also gives me 9. Because I got the exact same number here, because these limits are the same, that tells me that the two pieces line up. And so this function is actually continuous at x equals 3. So the only place where this function is not continuous would be at x equals 0. That's where those two pieces don't line up. So to summarize, with these piecewise defined functions, you're plugging in those endpoints to see if the pieces line up. That's the basic idea here. All right, let's do one more problem that's testing us on the exact same concept. This problem says, find k such that f is continuous for all values of x. So basically, this thing is going to be continuous if the two pieces line up. In other words, if the limit as x goes to 1 from the left equals the limit as x goes to 1 from the right. So just like above in the previous example, we need the two pieces to line up for this thing to be continuous. So what I'm going to do is I'm going to plug in x equals 1 on the top piece. So k times 1 plus 2. That's k plus 2. And then I'm going to plug x equals 1 into the bottom piece, and I'm going to figure out when would they be equal. What value of k would make those things equal? So let's see, 1 squared is 1. And so these two expressions are going to be equal when k plus 2 equals 1. And so that means when k equals negative 1, the two pieces in the function line up, and this thing is continuous. All right, that's it for this lesson. As always, let me know if you have any questions.